Hear my beep. Tells me we're running. At any rate, so you want to set it up and be clear about what you're trying to achieve. So in the background, that's how we want to explain what we're doing. How are we going to apply titration to get a K value? So, given a weak acid with known concentration, titrate or generate a titration curve with a known concentration of strong base. So we're looking at a strong base weak acid titration. Now strong base into weak acid gives a salt of that weak acid plus H2O. Now, of course, the salt is a cation anion of the system, and at equivalence point, no acid or base remain. Hypothetically, say NaOH plus the weak acid will go to sodium salt anion plus H2O. Everybody knows this, right? Now, in the titration, what's going to happen? Now, give yourself a little space over here because I'm going to make a point in this titration issue. You've seen, some of you have seen it before, maybe not. But what is going to happen in your titration as you add base, this will start about, not to scale guys, start about a pH of around 3 and will proceed to follow the standard looking titration trend through same, say that very high, maybe 12 and the max is 14 kind of thing. The equivalence point's right here. Regardless of what that equivalence point is, what I want to do is talk to you about the change in concentration of the weak acid as a function of addition of the hydroxide. At the point right here, A, at point A, the reaction has not, the titration has not begun. And so in the beaker, what we'll have is this arrangement. Just like we've been set up before. And we'll have the acid in the beaker and the base in the burette. Get me an acid and base color here. So, in the burette, we have a number of base molecules, sodium hydroxide. And in the beaker, you have this collection of acid molecules, weak acid, right? And as we add the the base into the acid, it's going to convert to the salt up here. Now, the salt is going to be purple. The acid is going to be red. And base blue in our legend there. So, what we're going to do is go through and make a titration. But before the titration begins, what I was getting at a moment ago is point A right here. We have 100% acid in the beaker. Right here. When we reach equivalence point, that's right here. How much acid do we have in the beaker? This is very important that you see this. Or you're just going to waste your time in the lab. At the equivalence point, how much acid will be in the beaker? Zero. Does everyone clearly understand that issue? If you don't, this is zero acid at that point. So what happens at B? You make that point B right there. What happens between A and B as you add the base into the acid? Well, of course, all right, we open the stopcock and we put some of the base in. And when the base, that one drop hits, it converts one of these to a salt. Yeah? So we have less acid in. So what's going to happen is we're going to start moving up this graph toward the equivalence point. And as we continue to add base, we will continue to convert salts, right? And so we're up to about, say, right here. Now, this is important in the next one. So if I add the next one, I will convert one more. That's going to be point C right here. What is the relationship between at point C, the concentration of the acid, anion, is what as compared to the anion concentration only. Okay? So we have an acid, and remember what's happening is we have a salt concentration here too. That's your anion. This is anion. And it's ionized 100%. So the dark dots are your anion. So we have 3 dark dots and 3 red dots, the acid. So what is the relationship between the acid and the salt there? The concentrations are equal at that point right here. That's called the VEQ over 2 point. And the VEQ over 2 point is where the weak acid and the salt of the weak acid have equal concentrations. Well, we continue the titration and you have to generate the entire curve. Now be sure you know what you understand what I'm talking about, because some of you in the last startup, you didn't even get to the equivalence point in that titration. You've got to get not only to the equivalence point, but I want to see the upper end of the shoulder up there. So when we add 3 more of these, we're at the equivalence point, right? So, wait a moment. There it is. Now we're here. That's the equivalence point. Only salt in the beaker. And so we've gone through the halfway point, the VEQ over 2, maybe titrate into there, and then we go right on. And then you want to continue. Now understand, the next drop of base that goes in does not have anything to react with. And so as you proceed past the equivalence point, this high pH in here is due to excess of base in the beaker. Yeah? See the point? Okay. Now, by generating this and the D2 curve, where you find the equivalence point volume, you take that and divide by 2. All right? I'll show you. I say we're through with this. Hang on. And go back and find that VEQ over 2 point. Analysis. From titration curve, VEQ over 2 gives HOAC concentration equal to O anion. I'm so used to using acetic acid. H anion is anion concentration, and we'll just say this is A minus, and this is HA right there. So the VEQ over 2, I'll try to keep this visible, is right here at point C. The thing we're looking for is the Ka value of the acid ionization, HA. When that ionizes, what happens? The hydrogen comes off, and we have this. So from this, we can write the expression for the acid ionization constant, which is H plus times A minus divided by the concentration that we started with of HA. At VEQ over 2, what happens is the HA equals the anion concentration. And as a result, at VEQ over 2, in the expression, we can cancel that out right there. And the hydronium ion concentration at VEQ over 2 is equal to the Ka value. However, in your titration curve, let me draw it one more time. You do not measure directly the hydronium ion. What you're measuring, is pH values. Of course, that's the equivalence point there. And this is what you're looking for. The pH at VEQ over 2. the pH at VEQ over 2, right here. So if the hydrogen equals a Ka, then we can take the minus log of the hydronium ion concentration and set the pH equal to the pKa. So once you get this pH at the half point, pH at the VEQ over 2, then you can say that pH at VEQ over 2 is equal to pKa. And the Ka is equal to 10 to the minus pH at that point. And this is what you use to get the numerical value of the weak acid. But it depends on you understanding how the VEQ over 2 relates to the ionization of the acid, the equation for calculating Ka, because at VEQ over 2 these fall out and leaves you with VEQ, the concentrations being equal at that point. But that's why they fall out. And the hydronium ion equals the Ka value there. But you're not measuring Ka value. You're measuring pH value. So you need to learn what is the relationship. Well, if H equals Ka, pH equals pKa. And then you use the analog to get the Ka value. Okay? You already have the solutions on the cart. I think they're given, I think, a H propionic acid, I believe, is the weak acid they're using. And you can look up or Google the Ka value, the accepted value, so you can do your percent error. I don't know what it is. I might know. Hang on. Yeah, I got it. Propionic, 1.3 times 10 to the minus 5. So you're shooting for that number. Okay, right there. Okay, you're going to have a 0.10 molar propionic acid, and you're going to have a sodium hydroxide concentration of 0.05 molar. You titrate NaOH in burette into 20 milliliters of 0.10 molar H pro. Generate entire titration curve and determine equivalence point. Using equivalence point volume, divide by 2 to get the VEQ over 2. Draw straight line from VEQ over 2 up to graph and over to pH at VEQ over 2, and finish by calculating the Ka value equals 10 to the minus pH at VEQ over 2. Do it 3 times. That's what I want you to do. And you know how to do titration, so you ought to be able to set this thing up and run through. I tell you what, let's just keep it 2. And that'll save us some time because we got one more to do. Hang on. I wouldn't know. It doesn't freeze over here. That's the only thing I couldn't figure out. For 2 titration results, calculate Ka, average Ka, standard deviation, confidence interval, and RR, range of reliability. Your conclusion, the Ka, the experimental Ka, was found to be blank, giving a RR of blank to blank. Percent error is calculated, in your, like that in your error analysis. Period. That's it. Now y'all will be able to handle that in your group pretty quick.